Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So hi, I'm going to present what I did during my PhD together with Luc Maranger at INRIA, Susmit Sarkar and Peter Swell at Cambridge University, I suppose. So if you start writing concurrent programs running on a multiprocessor, you may assume or would like to assume sequential consistency as the execution model, which says that the result of executing a program corresponds to an interleaving of the instructions that are involved on the processors. So I'm going to present several examples in this talk, all of them as tables. So the columns are processors, and here on P0 you have a write of value 1 into memory location X, followed by a load from Y into register R1. On P1 you have a write of value 1 into memory location Y, followed by a load from X into register R2. And we want to see what are the possible outcomes, assuming SC, sequential consistency, as the execution model. So I'm going to do 1. So we start by writing 1 to X on P0, then read in from Y, assuming the initial values for X and Y are 0 initially. Hence we have R1 equals 0, because we read the initial value of Y. Then we write 1 to Y over here, and then read from X. And since we wrote 1 to X before, we write 1 into R2, as in this outcome. If we execute P1, then P0, we obtain this one. And if we do the 2 stores before the 2 loads, we obtain this one, where the 2 registers hold 1 in the end. So here's the same program, but written in x86 assembly code. You have the write of value 1 into X, followed by the read from Y. Here, the write of value 1 into Y, followed by the read from X. And we're going to check on my machine what it says. So here's the test, the same that I showed you. And I'm going to run it against the chip of my machine with the litmus tool that mainly Susmit and Luc wrote, and send it into a result text file. So here's the test again. Here the actual assembly code that is generated and the memory states that were observed during the runs of the test. So we have the 3 SC ones and a new one, which is not SC, because we didn't obtain it by enumerating the interleavings of the instructions. So this means that the chip that's on my machine has a weaker memory model than SC. And indeed, for performance reasons, the modern multiprocessor can have weaker memory models than SC. So this means that to write correct concurrent programs, we need to understand what are these memory models. And we cannot rely on the documentation to do so, because it's written in natural language, thus ambiguous. And so this is not only a problem for low-level programmers, let's say, because you can observe the same kind of issues due to compiler optimizations, let's say. So in this talk, we're going to study 3 potential sources of weakness. The first one is out-of-order execution, as exhibited by the test I just showed you. Store buffering, where a processor writes in its own store buffer and can read the value written in the store buffer in advance, that is, before the other participants have access to it. And store atomicity relaxation, which is the case when 2 processors can communicate via cache that is shared by them only. That is, they have a secret space to communicate, to exchange values before the other participants have access to this value. So in this talk, I'm going to present the generic framework I developed during my thesis, which I wrote in the Cockproof Assistant, in which you can embed SC, TSO, PSO, and RMO. And TSO is roughly x86 models. model, alpha and a fragment of PowerPC. You can prove formally that the instance of the framework I developed and the native historical versions of SC, the Spark models and alpha are equivalent. But for podwr, there was no formal model before. So to design this model, we developed a testing tool, which helped us lead an intensive experiment against hardware. And I'm going to explain how we test the chip. And finally, we have formal results on the semantics and the placement of synchronization primitive in a piece of code to enforce a strong behavior to a program running on a weak mirror model. That is, you run, say, an x86 piece of code, and you want to make sure that it's going to have only SC executions. So where do you place locks, barriers, read modify writes to make sure that it's the case. And we have a tool as well that does that. So first I'm going to explain how I model executions of programs. So here's an example again. We have a write of value 2 into x on P0, a write of value 1 into x on P1, followed by a read from x into register R1. And we want to describe the execution where R1 equals 1 in the end. That is, this load read its value from the preceding store. And x equals 2 in the end, which means that this write was the last one to hit the memory. That is, this write occurred and this one afterwards. So first, I'm representing instructions by memory events. So a store of value 2 into memory location x corresponds to a write event with the same location and value. Similarly, on P1, we have a write event of value 1 and memory location x, followed in program order, which is represented by this relation, PO for program order, by a load from x into register R1. So we have the R direction for read, the location is given by the instruction, and the value of the read is given by the final state. So if SC was an appropriate execution model, this would be enough to describe executions of programs. But we need some more information to express the weakness that we are studying. So the first relation we need is what I call the write serialization, which is abbreviated as WS. So it's a total order on the writes to the same location, which represents the order in which writes to a given location x hit the memory. So because of the final state, we know that x equals 2 in the end, which, as I said before, means that this store of value 1 hit the memory before this one does. So the corresponding events are ordered in the write serialization. The write to x with value 1 is ordered before in the write serialization, the write of x with value 2. We need to express who reads from whom as well. So because of the final state, again, this R1 equals 1 means that the load there read its value from the store over here, which is represented by the read from relation, abbreviated as RF. The write to x with value 1 is in read from with the read from x with value 1. And finally, from these two relations, we derive last one, the from read map FR. So we say that a read, this one, for example, is in FR with a write. When the read read its value, that is, was in RF with a write, that hit the memory, hence what it in WS, the write, which is in FR with the read. That is, this read took its value from an older write from the memory point of view than this one. And so we gather this information in what I call an execution witness, which gives you the write serialization and the read from map. And the events, the program order, and these two relations are going to be enough to describe an execution. So now that we know how to describe execution, I'm going to explain how we describe models, I suppose, which I call architectures. So as I said, we are describing a generic framework, and each instance of each model of this framework is called an architecture. And the goal is to embed the memory events that arise in an execution in a single partial order, which represents the global view of the memory. And an architecture is going to filter the execution by saying which relations are embedded in this global view of memory and which are not. So the first filter we apply is the preserve program order, which is written PPO. So this is the initial example where we write 1 into X corresponding to this write event in program order with a read from Y. And on the other processor, we write 1 to Y over here in program order with a read from X. And we observed on my machine that this outcome is exhibited, which corresponds to this execution. That is, if R1 equals 0 in the end, this means that this read took its value from the initial state. That is, read from a write that hit the memory before this one. Hence, there's an FR relation between the corresponding events. And similarly, if R2 equals 0, this means that this read took its value from a read that occurred before this one. Hence, there's, again, an FR relation between the corresponding events. So the one explanation for this test is that the instructions on P0 and P1 can be reordered, which means that the program order relation on my machine between a write and a read is not steady enough to ensure that no reordering can occur. So, whereas in SC, you cannot reorder these pairs. This means that the fragment of the program order that relates write to read on TSO is not embedded in the partial order that describes the global view of memory. It's not in the preserved program order. Whereas on SC, it's the case that everything, the whole program order is going to be preserved, maintained in this order. The second relaxation we study is the store buffering. So in this test, we have a write to X with value 1, which is read from the store buffer by this read. And on P1, similarly, we write to Y in a store buffer, which is read from the store buffer by this read. So we have, to describe the reading the value from the store buffer over here, we have a read from relation between the corresponding event, which is an internal one, that is a read from that relates to event from the same processor. And similarly for Y, this store corresponds to a write to Y, and this read reads its value from the write. The read is there, and there's a read from relation between them, an internal one as well. On SC, store buffering is not allowed. Therefore, this non-SC outcome won't be observed, because, again, the read from relation that are there are global. That is, they are embedded in the global view of memory. Whereas on TSO, for example, this is allowed, which means that the read from relation cannot be observed by the other processor. I won't embed the read from relation in the global view of memory. I take it off this partial order. So I'm going to write GRF, global read from, for the fragment of the read from map that is considered global by the architecture. And on SC, every read from relation, that is communication relation between a write and a read, is going to be in this global view, whereas on TSO, the internal ones that corresponds to the store buffering are going to be out. So the last one is the store atomicity relaxation. And again, we play with the read from relation, but external ones this time. So on this example, we read from X, then from Y on P0, corresponding to these two events. On P1, we read the same locations, but in the converse order. That is, we read from Y, then from X. On P2, we write to X, which is over here. And on P3, we write to Y over there. And so this outcome, or this execution, corresponds to the case where P2 writes 1 to X, which is read by P0 on a cache that is shared by them only. That is, P1 does not know yet that X equals 1. X equals 1, yeah. So we have R1 equals 0 on P1 over here. That is, P2 and P0 communicated via X secretly. And similarly, P3 writes to Y, which is read by P1 on a cache that is shared by them only, before P0 has access to the value. Hence, R2 equals 0 on P0 here. So the communication between P2 and P0 is described by, via X, is described by the read-from relation between the corresponding events. This is an external one between two distinct processors. And same on between P3 and P1, we have an external read-from between the corresponding events. So this is obviously not allowed on SC again, because there's no secret communication via caches allowed. But on POWER, for example, you can observe this outcome. And we explain this in this model by the external read-from not being embedded in the global view of memory, which abstracts and models the fact that two processors can communicate via a cache shared by them only.
Could you just read the meanings of the abbreviations, DP,
sure.
RFE, and GRF?
So GRF is, RF is the read-from. GRF is the global read-from, that is the fragment of the read-from that is supposed to be global, that the architecture defines as global, meaning embedded in the global view of memory.
I see, read from global memory rather than local cache.
No, not quite. So I'm going to describe the global view of memory by a single partial order. And this is going to be the fragment of the read-from that is embedded in this partial order.
All right, so it's a fragment of the global partial order.
Yeah.
Okay.
So
equals empty
means that no read-from is going to be considered global on POWER.
Everything's done by RFI and RFE on POWER, is that what you're saying?
Yeah, exactly. That is, you allow store buffering and that kind of communication via caches.
And what does RFE stand for?
So external read-from, that is read-from but between two events from distinct processors. Whereas RFI is between two events that belong to the same processor, internal read-from.
But an RX0 and an RY0 without any read-froms at all.
Say that again?
You have RX0 at top right and RFY0 at top bottom left.
Yeah.
Without any read-froms at all.
So if you recall the definition of FR, this means that this read took its value from a write, in this case the initial one, so I omitted it. Took its value from a write that hit the memory before this one does. So there's a hidden read from the initial state, which is in WS write-serialization with this one.
So I can deduce that from the FR.
Yeah, exactly. And so DP stands for dependency. So yeah, what I didn't say in this case, that there is two reasons for this outcome to be exhibited. Either the one I presented you, the communication via caches between P0 and P2 and P1 and P3 respectively, or the reorderings of the reads on P0 and P1. So if you create a dependency between the two loads over here and the two loads over there by, say, having a XOR on the registers, this outcome is still going to be exhibited on POWER because of the secret communication via caches. So that's why DP stands for, assuming I did a XOR to make the dependency.
This could happen anyway if we're allowed to swap the P0.
Exactly, yeah.
But even if we're not, it can still.
Yeah, so there are two reasons for this to be exhibited. Okay. So now an architecture, as I said, is going to be a filter. So it's going to give you three functions that take executions and give you relations. The first one computes the preserved program order over an execution. That is the fragment of the program order that is going to be embedded in the global view of memory, that is going to be maintained in this order. And the fragment of the read-from map that is global, which is whether store buffering is allowed. In this case, I don't embed the internal read-from in the global read-from. And whether store atomicity is relaxed, that is, whether secret communication via caches is allowed. In this case, I don't embed the external read-from in the global read-from. And the last one corresponds to the barrier semantics, which I'm going to explain later on. So now we know how to describe an execution and an architecture, so we are ready to define what it means for an execution to be valid on an architecture. So I keep mentioning a partial order that corresponds to the global view of memory. So here it is. I call it the global happens before, defined with respect to an architecture A. And it's merely the union of all the relations considered to be global by the architecture. That is the preserved program order always, the right serialization, the from read map, the fragment of the read from defined to be global by the architecture, and the ordering enforced by barriers. So the main validity condition of an execution in an architecture A, of an execution EX, where E is the events and the program order, and X is the communication relation, corresponds to the acyclicity of this relation. So this means that there's a global timeline in which the writes hit the memory and the reads can be embedded in this timeline as well, in a total ordering fashion. So a few examples. So here's how we describe SC in this framework. So we need to define the preserved program order and what fragment of the read from is global. So on SC, no reordering is allowed. So the preserved program order is the whole program order, and no store buffering or store atomicity relaxation are allowed. So all the read from are global as well. No secret communication is allowed at all. So again, this is the same example. And now we can prove that this outcome is not allowed on SC without enumerating all the interleavings, just by showing that exhibiting a cycle in the global relation for SC. So we have the write to X with value 1 there in program order with the read from I, the write to Y with value 1 here in program order with the read from X. And as I said before, since R1 equals 0, this read occurred before this write, hence the FR relation between them, and similarly for X, there's an FR relation here. So since the whole program order is preserved, these PO relations are global, and the from read relation is global as well. Hence we have a global cycle in this execution, which forbids the execution in SC. On TSO, we can relax, as we observed on my chip, write to read pairs. That is, these two pairs of instructions are not going to be maintained, or may not be maintained in the program order, which means that I take off the PO relations here and here of the global relation, and there's no cycle, no global cycle anymore, which means this execution is allowed. Right, so here's the whole validity condition. So there's the existence of a global timeline of memory event, which is modelized by the acyclicity of the global relation. There's what I call the uniproc check, which checks if SC holds per location. That is, if you take a look at your program from the point of view of one location, then the value that this location can read IC are reachable on SC, more like. And the thin air check forbids causal loops. So, and now I'm going to explain, how we do testing. As I said, we can prove that for existing formal models, such as SC, TSO, alpha, each instance of the framework, the corresponding instance of the framework is equivalent to the native definition, but we needed to test both the chips and our tools, so we designed a testing tool. So again, the same example, and the non-SC execution, we know now that it corresponds to a cycle in certain relations of my framework. So we are going to reverse the process, and from a given cycle of relation in my framework, we are going to build a test that's going to exhibit its outcome if one of the relation is relaxed. And if we target in a clever way only one relaxation at a time, we can precisely state why the test exhibited its outcome. That is, diagnose kind of the weaknesses that a chip exhibits. So, for example, in this case, we know that the reason why this outcome is exhibited is that the pairs of instructions can be reordered, which the write to read pairs, for example, in program order can be reordered. That is, this test targets the weakness exhibited by this relation. So if I want to, conversely, build a test that tests whether write-to-read pairs can be reordered, I'm going to target this relation in the input cycle of the tool. So given a cycle of my relations, which needs to be refined a bit to carry more information. So in this case, instead of just program order, I specify that the two events are two distinct locations, hence the D here. The first one is a write and the second one a read. And for the communication relations, write serialization, read from read, I need to add the information of them being internal or external between two distinct processors or the same one. So given this cycle, I can build the test I showed you. So first I set the directions. So the arrow here tells me that the first one is a write and the second one a read. From read is by definition between a read and a write. And again, this one tells me that the second one is a read. And from read by definition relates a read and a write. Then I set the locations. The first event I meet, I give it a fresh location X. The D over here tells me that the second one has a fresh location Y. FR is between two events with the same location, so I just propagate Y. Again, this D tells me it should be a fresh location Z, and because of FR, we can unify Z and X over here. Finally, we set the values. First, the values of the write. So the first write I meet to a given location X, I give it the value 1. If there were a second, I would give it the value 2, etc. And the first write to Y I meet, I give it the value 1 again. So the values of the write give us, at the same time, the write serialization for this test by just taking a look at which value is in the write. And the values of the read, reads, I can deduce from the definition of the arrows of the relations. So this read is in FR with a write, which has the value 1, which means this write is the first write in the write serialization. So this means that this read takes its value from the initial state. So I give it canonically the value 0, and I should record that in the test that I'm building, Y equals 0 initially. Same for X. X reads this read from X from a write that is before the first write to X. So it reads from the initial state with value 0, and I should record this information. So as I said, by setting the values of the read, we decided that X equals 0 and Y equals 0 in the beginning. And then to a given event, I associate an instruction with the same location and value. So a write event to memory location X with value 1 corresponds to a store with the same location and value. The arrow here is a program order 1, so I know that I should carry on building my thread with a read from Y with value 0. So I associate it to a load from Y, targeting a given register, and the value of the read over here tells me that in the end, the value of the register is 0. So I'm building the final state by the values of the read. Then the E over here says that these two events do not belong to the same processor, so I should start building a new thread here, which I do. So to the write event, I associate the corresponding store in program order with a read from X, targeting a given register, which value is given by the value of the read. So from a given input cycle where I only specify the relations I'm targeting, I can build a test which outcome is going to be exhibited if one of the relation over there is not global on the chip. So yeah, to test chips, we build two kinds of tests. So the relaxed ones are built from cycles that contain a particular relaxation that we want to test. In this case, whether write-to-read pairs can be reordered. And all the other relations are supposed to be global in the framework, so that we know that there's only one reason for the test to exhibit its outcome. And to test our assumptions of the global relations, on the global relations, we also build safe tests, which shouldn't exhibit the outcomes. And they come from cycles of only global relations in the framework. And if they break, we know that there's an issue in the model. So for example, on TSO, we know that write-read pairs in program order can be reordered, and store buffering is allowed, which is in the framework modelized by these two relaxation. So write-to-read pairs in program order with distinct location and internal read from. So we are going to build tests that targets these two relaxation, all of the other relations being global. And all the safe tests, the safe tests will contain all the other relations. So I'm going to show you how we do that. So we said that we wanted to test whether write-to-read pairs in program order can be reordered. So I write a configuration file, which specifies the architecture of my chip as being x86. In this case, I want tests up to 6 processors, where the size of the input cycle is at most 10. That is, the number of arrows is at most 10. I want to name them with a common prefix. I want to test whether this particular relaxation, assuming that this one is global. So I run the tool against this configuration file, which gives me 4 tests. The number of tests depends on the bounds I set on the number of processors and the size of the cycle. So the first one is the one we already saw, the one I presented. And the second one, for example, is going to be the same, but replicated on more processors. So we have 3 processors in this one, all of them starting with a write to a given location, followed by a load from a distinct one. We want to test the internal read from as well. So we, again, write the same kind of configuration file, carefully recording what are our assumptions on the safe, on the global relations. And finally, we need to test our assumptions on the global relations. So we just build, again, the same kind of configuration files, where nothing is specified to be relaxed, but all the one we want to test are assumed to be safe. And we build all the cycles, all the tests up to the bound specified that test whether these relations are safe or not. So, and this obviously yields far more tests. So we used this tool to test 3 generations of power machines. The first one is a power G5, the second one a power 5, and the last one a power 6. And we generated many tests and ran them many more times. And so the power G5 and the power 6 did not disagree, let's say, with our model. That is, they did not invalidate our model. Whether the power 5 exhibited behaviors in contradiction with our model, but after discussion with IBM staff, we understood it to be a power 5 implementation error. And so here's the fragment of a power model we developed according to the testing, which is only sound with respect to the testing we've done. So no preserved program order except between, that is, the program order is not maintained except between read-read and read-write pairs that have a dependency between them, say a XOR between the 2 accesses on the registers. No read from is global, that is, store buffering and the store atomicity relaxation are allowed. And the barriers are cumulative in a sense that I'm going to explain in about 2 slides. So, yeah, I'm going to give you a few words then on synchronization. So, recall the definition of an architecture. It specifies the fragment of the program order that is maintained and the fragment of the read from that is supposed to be global. That is, we can compare 2 architectures, A1 and A2. So we say that A1 is weaker than A2 when A2 preserves in program order at least all the pairs that were preserved by A1, and A2 authorizes less secret communication via store buffering or caches than A1 does. And we I mean, it's almost trivial to show that validity is decreasing. If you write a program or an execution that is valid on a strong architecture, it's going to be valid on the weak one, on a weaker one. That is, if you write a program that is valid on SC, it's going to be valid on POWER or x86. But the converse is not always true. That is, you can, as we did, write a program that has more execution on x86 than on SC. And we examine the problem of placing synchronization primitives in a piece of code by examining the converse way. That is, when an execution is valid on a weak architecture, whether it's going to be valid on the strong one. And this is going to be our goal by placing synchronization primitive. We want to ensure that the execution of our programs have this property. All the weak executions are actually only strong executions.
Again, I forgot what validity is.
It's mainly the acyclicity of the global timeline, together with 2 other checks. So we already saw this test before, which corresponds to, so this outcome is non-SC because it corresponds to this execution where you have a cycle in the global relation for SC, which forbids this execution. So it's the test where P2 writes to P0 via X secretly, and P3 writes to P1 via Y secretly. And as I said, there are 2 reasons for this test, this outcome to be exhibited. First, the reads on P0 and P1 can be reordered because the program order relations here are not in the preserved program order on POWER. And the second reason is the communication between P2 and P0 over here being hidden to the other participants, and similarly between P3 and P1 over here, the read from being hidden to the other pair of processors. So we need barriers that will forbid these 2 weaknesses. So I'm going to try first semantics for my barrier. So I place it between the 2 reads here, assuming that its semantics is only to prevent the reordering of pairs. That is, I create a global ordering between the read from X and the read from Y on P0, represented by this red arrow here, and I create a global ordering between the read from Y and the read from X on P1, represented by this red arrow here. But this is not enough, as we said, because the communication between P2 and P0 over here, for example, is not global. So we still don't have a global cycle that will prevent this execution. So we need stronger semantics for our barrier. And the semantics we designed is what I call cumulative, which does not quite correspond to the POWER cumulativity, but still. So the barrier over here will enforce a global ordering between the write on P2 and the read there. So we said that we want to create a global cycle, so we could just decide that the semantics of the barrier is to make the communication between P2 and P0 over here, the read from relation here, global. But this would be really costly. This would mean that the barrier flushes the cache even before, that the barriers make this communication between P2 and P0 global, that it makes it public. Whereas in this case, we don't forbid the secret communication, but we enforce that the value of X is flushed and published, let's say, before the second read starts. So instead of making, so this writes into the cache, this reads from the cache again, but before the next instruction starts, we flush the cache, which means that this value here, this write here, is globally ordered with the second read. Similarly between Y and X, so this writes in the cache, this reads from the cache, and then before the second instruction, this one starts, we flush the cache, which makes a global ordering between the write and the read. And therefore we create a global ordering, a global cycle, in the execution, which will forbid this execution. So we prove that if the barriers provided by a weak architecture A1 have the following semantics, then we enforce stability. That is, all the weak execution are in fact strong ones. So the barrier provided by an architecture A1 will restore a stronger one A2 if they restore the pairs that are preserved in program order on A2 but not on A1. That is, they compensate the weakness of the preserved program order of A1, which is described by this piece of math. And secondly, they compensate the fact that some writes may be performed in caches and store buffer on A1 but not on A2, and they flush it appropriately at appropriate times. And so we tested power sinks intensively, and we found no mismatch with this semantics. And so, yeah, here's the statement of the theorem. So if you have a weak execution and you place your barriers with the appropriate semantics in the execution, then you make sure that the execution is actually valid on the strong one. And so we do this for different kind of conflicts, either the pairs that I presented you, the preserved program order pairs, or the non-atomic writes, but we also have the same kind of formal study for data races and locks. So from this theorem, we designed mappings to ensure that all the executions of your program are going to be SC. That is, you spot the pairs which you want to synchronize in the code and map them to the same pairs where you included a barrier in between them. So we show how to use even the weaker barrier on power. And we do it for x86 as well. So
will this be a global analysis of the whole program?
Say that again?
Is this a global analysis
Yeah.
of the whole program?
And we assume the memory location are constant as well. So let's say we want to synchronize the test I showed you. So we have a read from X followed by a read from Y. Here, a read from Y followed by a read from X. Here's the write to X, and here's the write to Y. This is the same test, but with the processor being shuffled a bit. And so we want to put, say, barriers in this test. So I specified the write option, which is fence in this case. And this gives me the same test, but where we added barriers, the one that I showed you on the drawings, in appropriate places. Sorry. And then, so we do it as well for log-free primitives. So FNO here stands for fetch and no-op, which corresponds to an atomic load. That is, it's a read, modify, write primitive where you load and store the same value but in an atomic fashion. And we show that in this case, we can, we show that this other mapping ensures stability as well. That is, if you apply it to your code, it's going to have only SC execution. And so, again, the tool is able to place these primitives in the piece of code. So it just adds, following the mapping, replace the first read by an atomic one, places a barrier over here, and again on P2, replace the first read by an atomic read and places a barrier over there. And so we designed several mappings. So F is for only placing barriers, the one that I presented on the example. A is places some read, modify, writes on reads and writes. P is the one where you place only read, modify, writes on reads and add barriers to compensate for other stuff. And L corresponds to placing locks on data races. And we compare their productivity only on a few tiny tests. But this shows that the locks are really extremely costly. Sorry, X is the test without any synchronization. So we measure how much outcome we observe per second on the test without synchronization at all. And the lock mapping productivity is really worse, whereas the 3 log-free mappings, the one where you place barriers and the 2 where you place read, modify, writes, are comparable and not that costly, actually. We do it for power machines there and x86 machine over here.
So the X column is producing non-SC behaviours.
Yeah.
And the others are all SC behaviours.
Exactly.
in different forms,
Yeah. And yeah, we have experimental reports of all that kind of stuff on the web. And we do measurement. We measured a bit the time of a synchronization primitive. So you can see that on power, sync is extremely costly as compared to the weaker barrier LW sync, but that the atomic stuff, the atomic read modify rate things are really even more costly than sync. Whereas on x86, the cost of the barrier and the read modify rates are comparable. And so, yeah, finally, a few URLs, I suppose. So all of our results, the equivalence proof between models and instances of my framework, and the synchronization placement proofs, etc., are done in Cox, so the development is over there. And the testing tool can be found here with our reports on testing the power machines and sources of the tests and documentation. And the synchronization tool, again, with sources and documentation, can be found here. And the report on timing and productivity experiments. Yeah.
The results, that XFA, could you show that again?
Sure.
It seems to show that SC is not very expensive if you do it right.
So, as I said, we did this on a test bed that is not really significant. We only tested litmus tests, not that many of them, but yeah, if you trust this test bed, I agree.
You don't trust it?
I do, but in the sense that I guess it's a representative test bed, but we had complaints that it was not real world enough, that people would like to test the tool on real world program, which is not possible yet because it's only a prototype.
I wonder whether you could get away with just taking some random power assembly program and rewriting the assembly for some of these.
Yeah, I suppose we could, yeah.
Because the mappings are simple enough, you might be able to get away with it.
So the plan was more like, so there's a compiler by Lee and Podwr where they use only the sync barrier. So the plan would be taking their compiler and modifying the appropriate part of the compiler to use our mappings instead of theirs, which are naive, where we studied it a bit more, if that makes sense.
Yeah, but it might be more convincing to take an honest, this decade
Yeah,
power
I agree,
program.
yeah.
Maybe quite a large one.
So I agree, but again, we could argue the other way, that if we can prove some, say, completeness of the test bed, even if it's on tiny litmus tests, that it's significant enough. It would be another way of arguing, and that's why I trust this test bed, but yeah.
How long does it take to insert the barriers on? What's the sort of time frame?
Say that again.
How long does it take to work out where to put the barriers? Sort of how does that grow with the size of the program?
Oh, I don't know. Luc, maybe you do? I'm not sure.
Most of the analysis, let's say, the barrier from Lee and Podwr, and this is standard data flow analysis. Although our implementation will be the best one, I think it can be done quite fast. The real problem is that you have to follow some technique to approximate all the cycles
Yeah.
of the test. And this is what we do in this prototype too. In some real compiler, one would make some conservative approximation
Of the
this,
cycles, yeah.
and then the only possible answer is that you have to do it and try. Because the number of cycles infer quite a lot.
Yeah.
But for small example, there's no problem.
Yeah, as I showed you, it's immediate on the tiny ones we have, but yeah.
So, how do you? I mean, is there some way in which you can understand whether you've thought of all the possible explanations for the behaviors that you actually see? Like, suppose you hadn't thought of the possibility of power to communicate rights between two processors and not globally.
Yeah.
So, what would you see something strange when you look at the model, or when you observe test results?
Yeah,
To say that there's something going on that we haven't understood yet.
That was the case, I think, for the external read from, I suppose. At the beginning, we, or at least I think, thought that IR-IW was exhibited only because of the reordering of reads. And after placing things like dependency between them, it was still exhibited. So, yeah, but that's a matter of going back and forth from the testing to the model and debugging the model. But yeah, sometimes we observe tests and we're like, I don't know why it's exhibited. So, yeah. And you have to work more on your model and tweak it. Yeah. Or even invent another kind of model, as Smith did afterwards.
That's what your safe test do.
Exactly, yeah. That's a safety check on the model. They didn't fail. That's all I can say. Or safe tests.
I have a question on the completeness of testing. So,
yeah.
From what I understand, you take cycles and you generate a very simple concurrent program, and then you run it many times.
Yeah.
In principle, you could assume that if you use different registers or different constants, or if you add garbage instructions in between,
yeah.
or if you run them together instead of separately, then something else will happen. Are you trying to do that, or is it something that's
so?
Just
no, I thought of completeness from two other point of views, and yours is a third. So there's the whether you generate indeed all the possible cycles, since our tests come from cycles, and actually you can show that there's a bound to the cycles you have to generate, so that's the first one. The second one would be, so given we have data over the number of runs we need to exhibit weaknesses on a chip, and I would like to deduce some kind of probabilistic distribution on the number of tests I should run, the safe ones, to make sure they are safe according to this bound. That is, make sure that if I run these safe tests, n time n coming from the number of the relaxed test, then I'm safe, kind of. And no, I didn't think of your suggestion. Did you, Luc, maybe? I don't know.
Yeah, of course, but the original assumption is that it does not depend on that. So for the value, I guess it's a reasonable assumption that the behavior does not depend
on the value.
For the values of the addresses, for
no, but the garbage collection things.
Having some instruction, extra instruction. Of course, if there is a specific bug in the processor, this may or may not uncover the bug. So we are not targeting this. Because obviously if you can have any kind of number of extra instructions, or consider any addresses or any parity, whatever addresses, the set of tests is infinite. It's not infinite in practice. You see what I mean? There's no...
But nonetheless, you could randomize a little rather than use exactly the same test.
Yeah, you can. But yes, you can. But if you do randomize, you are not complete. So, what I want to say is that that's our main objective was to test the memory model.
And to do model exploration, I suppose.
Regardless of values or whatever. The bug was that.
For example, if you write 0, then it's quite likely to be special, at least in some processor sets.
So when we find a bug, we try with different values.
Yeah. But it depends what you're testing for, I guess. But we were mainly exploring the chips and our models until now.
Amount of randomization, for instance, for the addresses.
Processor core choice. One of the some architectures have are irregular, right? Where the cache, the memory resolution is done hierarchically.
Yeah.
So processes interact differently, whether they're close or
far
apart
away.
in the resolution tree.
Well, there are a lot of random things in the testing bed.
But again, the processor being far or near, and it being observable. We didn't care about it because we just abstracted by our read from relation either being it's a switch, a Boolean switch, like either they are in the global order or not, and we didn't modelize any hierarchy over these read from relations.
Well, it's supposed to be invisible, right? But of course, if there's a problem,
yeah, exactly.
Again,
It's not actually invisible.
No,
it
yeah.
should be, I think it should be understood that we don't look for processor bug.
Yeah,
We
no.
want to have the memory model of the machine, and it's going to be over. And that generally, if we find a bug, it's a bug in the memory model, and it does work. Assuming there's no bug at all by testing is something we don't really target.
You don't want to write programs where you depend on two threads being close together.
Yeah, no.
no.
From this point of view, we're quite predictive. Jade said that she was understanding things by testing, but I mean, we are all doing that. We had no idea at all on how this could work.
Yeah, I didn't, at least. Yeah.
We still sometimes have no idea. We have a model, but we don't know exactly why. So it's just an abstraction. And Jade says there's a secret hash. That's a way to understand why
yeah.
it is so. But you know there are other things like interfering.
Yeah, exactly.
And the surprising thing, this is Jade told, but I think something in this model that is a real novelty and that does not appear at first is that this kind of model, first we have this normality model, is the first one to handle the non-atomicity of stars by making this GRF relation. And this is some kind of innovation because this is a global time model, quite simple attraction, and we have a way to account for very weak architecture. And I think this is an important point, one important point of this modelization. But it was a comment.
I hoped you were going to show us that SC was impossibly expensive and so that we could all have a lovely time designing non-SC programming languages. So we've really disappointed you.
I'm sorry.
You still can do it.
Oh, yeah.
Any more questions? Then let's thank Chad again for
Thank you.